Okay, so if there are none, let me go on. So I started talking about uncertainty principles. Haven't yet said what is that. So let's look at, so let's recall. So G is a finite abelian group, and let's capital N be the size of G, cardinality of G. G hat is its dual. Of course, it also has the same cardinality. And we have so far seen the duality relationship and Plancherel and all that. So for a function in L2 of G, we obtain f hat in L2 of G hat, its Fourier transform by f hat of chi is just f in a product chi over square root n, which is given by this formula, the second formula here. Okay, f hat of chi equal to 1 by root n summation fx chi of x conjugate. And the way you recover f from f hat is almost the same because of the duality. So fx is just 1 by square root n summation f hat of chi chi of x. No conjugation here. So that corresponds to the fact that f hat is not f, but f hat check is f, right? So that is the why there is no conjugation. Now, so with these formulas, now I recall this LP norms. Norm FP is defined as fx to the p to the 1 over p. So by the way, just let me say that it's a norm when for 1 less than equal to p less than infinity, and for infinity we have this sup norm. But we may use it, so we can also use it as long as you know it is not a norm. We will use this and even maybe even refer to it as can also be used for 0 less than p less than 1. Okay. So let me just write this properly here. For p less than 1, it is not a norm. Okay, so it's not a norm, but nevertheless, so it can be used, just not as a norm. You can use it to measure the size of a function if you want. Okay, for p less than, we will use, I mean, I won't use much, but I'm saying that we can use also, but it's not a norm. So we just use it to measure the size of a function. It is some measure of the size of a function. Okay, so well, it's not a norm though. And just to caution, it doesn't even give a metric. So if you were to use, so remark, when I write this, I mean exactly this formula. So in some books, another thing is done, which is to take this. So in some books, so this will never form a norm, but if you raise it to the power p, oops, 1 second. If you d of fg equal to for p bigger than 1, greater than equal to 1, this gives a metric because this is a norm, the difference will give a metric, but for p less than 1 gives a metric. I mean, it's just a remark. If you want, you can check it. It's not a difficult point, but it is not. But that's not what I am using. I'm not raising it to the power p. I'm using, for me, this norm p will denote this same quantity. Okay, it's homogeneous. The thing is, raising to the power p will lose homogeneity. 2 times f, then 2f and 2g, their distance is not 2 times the distance between f and g here. So it will be 2 to the p times the distance. So it's a, but it can be used to give a metric. Okay, so this LP for 0 less than p less than 1, they are not good as spacers, but measuring the size is okay, perfectly no problem. Okay, you may want to measure the size of a function like this, not an issue. Okay, so now let me come to the main point. So the key observation about f and f hat is the following. Okay, so you take f, this function f, the first expression, you look at the first expression for f in terms of f hat here. So put absolute value of f of x. It is bounded by 1 by square root n sum of absolute values of these quantities, whereas chi of x has absolute value 1. So you just get sum of absolute values of f hat, which is exactly the L1 norm of f hat. So we immediately get the L infinity norm of f is bounded by 1 by root n, because I had put a 1 by root n here, the L1 norm of f hat. And exactly the same way from the second one, from the second expression for f hat in terms of f, we see that the L infinity norm of f hat, which is the supremum of absolute values, is bounded by 1 by root n times the L1 norm of f. Okay, hold on. I forget whether I started recording or not. Okay, I have started. Okay. So we have both these inequalities. Is okay. So this itself. So now I say that this is actually. So what does this tell us? So from this we get one uncertainty principle like this. So we can say, suppose we multiply the two of this together. Okay, suppose we multiply the two. So first, so this is the first uncertainty principle that I will say. What is happening here? Sorry. The orientation is not being okay for some reason. Yeah. Anyway, I will. So what is the uncertainty principle that I want to say? Suppose I divide by this and multiply this. So what I have is, so yeah. So what I do is, times let's look at this quantity. What can we say about this? On the first factor is the L1 to L infinity norm ratio of f. The second is the same L1 to L infinity norm ratio of f hat. By the way, I'm just writing 1 and infinity here to indicate L1, L infinity. But of course, you understand that on for this one, it is L1 of G, L infinity of G. Here it is L1 of G hat, L infinity of G hat. I'm not going to write like that. I think from the nature of the function, it is clear what is the domain and what norm we are taking. If it's not, then I would write L1 of G, L1 of G hat and all that. Okay, so we have this quantity. So what can we say from here? You see the L1 norm to L infinity norm of f hat. So norm f1 divided by norm f hat infinity beats square root of n. Okay, L1 norm by L infinity norm of the Fourier transform beats square root n. Similarly, L1 norm of f hat divided by the L infinity norm of f will beat square root of n. So this is greater than equal to square root n into square root n, which is n. Okay, so this is an answer. I claim this is an uncertainty principle. Okay, what is an uncertainty principle? Uncertainty principle says that both f and f hat cannot be localized. Okay, so what is the general? An uncertainty principle generally means that a meta statement that f and f hat cannot both be localized. Localized or concentrated, whichever. So I want to explain how, I mean, what that means and why this is actually measuring anything like that. See, whenever you take, so what is localized? For example, a delta function is very much localized. A delta x x naught is localized at one point. Yeah, it's supported only on one point, right? All its norm comes from one point actually. So it is localized, there is no doubt. On the other hand, the constant function is not localized. It is spread out, its norm is spread out all over the whole space. Any character is not localized because everywhere chi of x is 1, right? So for all x. So that means you take any of the LP norms, its contribution comes equally from all the points. So it doesn't come from 1 point or 5 points or such things. So these are not localized, whereas a function supported on 1 or 2 points is kind of highly localized. In continuous setting, it is a bit more clear. Continuous setting, I mean, so a function like this, if you take a standard example would be a Gaussian function in continuous space. In R, a standard one we take is e to the minus 2 square over 2 sigma square over sigma root 2 pi, which is a probability density, the normal probability, Gaussian probability density. So as sigma goes to 0, more and more localized. Then it becomes more and more peaked like this. Whereas when sigma goes to infinity, it is more and more spread out. Spread out is the opposite of localized. So then the function becomes kind of widely spread like this. Okay, so that's the general idea. So the intuition you can keep in the continuous world also. So that's fine, except that. So that I hope is clear. But why would I call this an uncertainty principle? Okay, the proof was just one line, but what is the point? Here is something that you may have seen definitions of L1 and LP norms, but what does it actually mean? What is one of the uses of LP norms is to measure this kind of thing. Yeah. Question?
So in the Gaussian example, so the Fourier transform will also look like a Gaussian, but with variance 1 by sigma square. That's what
That's
you
right.
meant.
That is
Right?
exactly. Yes, that is very much correct in the Gaussian case. But I'm not at the moment talking about. I mean, I just gave this as example of what localized function looks like. I'm not talking about for uncertainty principles in continuous space because formally speaking, I have not defined Fourier transform and so on. But what you say is right. There will be uncertainty principle that the function and its Fourier transform cannot be localized. It is seen an illustration in the Gaussian that its Fourier transform will have variance 1 over sigma square. If you increase one, the other one will decrease and vice versa.
Thank you.
Any other questions? Okay, so in general, the point I want to make here is that this is easy to prove, but you should understand what it is telling. Then only it will make sense. So if P and Q are two, if P is less than Q, you can take if you want if you are more comfortable thinking in 1 to infinity where it's norm, you can think that, but that's yeah. Anyway, my point is that this one can be taken as a measure of the the spread. Okay, so it's a measure of the how much the function is spread. Okay, or is it the other way? What should I say? Yeah, no, this is the measure of the spread. Why is that? So example, take P equals 1, Q equal to infinity. Okay, so what does that mean? So F1 is summation mod x in G, whereas infinity is just the maximal one of this. So when are these equal? For example, when are these equal? It is clear that norm f1 greater than equal to norm f infinity, because this sum also contains the maximum. With equality, if and only if f is a delta function. See, if it is not supported at just that one point where the maximum absolute value is achieved, then you will get more in the L1 norm, right? So in that sense, you see the ratio, in some sense, the smaller the ratio, the more localized it is. Okay, the smaller the ratio of this one norm to infinity norm, the more localized it is. Similarly, if in fact, so if fx is constant, that is maximum attained everywhere, then the function is far from localized, and then the L1 to L infinity norm ratio will show it. L1 to L infinity norm ratio will be n, because fx is, let's say f is constant function, L1 norm is n, L infinity norm is 1. So the L1 to L infinity norm shows the sort of localization in this sense. If it's localized, it is 1, if otherwise it can be as large as n. Another example is, you can take p equal to 1 and q equal to 2. Okay, so now you look at the reverse. Okay, the reverse, this is the reciprocal. Okay, I'm just taking the reciprocal rather than, so I should write that. So I'm taking reciprocal. This one. So let's just take a monotone transformation of this, namely square it and subtract 1 by n. I want to interpret it. That's why I'm writing it like this. When you do this, you see that this is actually what is it? It is, you can write it as norm f1 square n times norm f1 square n times norm f2 square minus norm f1 square, right? Which for me the most convenient way to think is like this: 1 by n norm f2 square minus 1 by n norm f1 the whole squared divided by 1 by n norm f1 the whole square, right? So what is this actually? What is the numerator? What is the denominator? So you recognize what are these quantities? See, oh sorry, I made a mistake here, I think. Is it so I divided this by n squared. So then I have only one. No, so something I made a mistake. What is it? Hold on. What did I do? There was n times f1 square, and I have divided this by n square, right? In the numerator, I divided by n squared. I got a 1 by n here and 1 by n square. Here also I divide by n square, so it's not okay. So there is an extra factor of n here. Okay, that's not a problem. It's a constant. That's okay. So we leave it at that. But what is this quantity? It is the variance of f, right? This is the second moment. I mean, so the variance you have to take 1 by n. So it is the average of the squares minus the square of the average. Variance of f divided by mean of, okay, I'm taking f to be positive, let us say. Otherwise, it's variance of mod f and mean of mod f. Okay. So this is n times mean square. So this is like, this is the coefficient of variation. if you have ever seen that. But if you haven't seen, see the variance coefficient of variation. Yeah, you divide variance by mean square to get a dimension-free quantity. I mean, if you say variance is big, I mean, how big? I mean, you have to compare it to something. So standardization is variance by mean square gives you a dimension-free quantity, which so this is a standard measure of spread. That is used in statistics. Okay. So the more it is, the more spread out a function is and such things. Okay. So so that is the meaning of all this. Okay. Yeah. Anyway, so that way, this is an uncertainty principle. Is okay? I mean, any questions, comments here? I just tried to say how LP norms. So there are many problems in mathematics which say, which is about proving something is sort of close to uniformly distributed. Usually there is a sequence of functions or something becoming uniformly distributed on some set. So there are many big open problems of that nature. And one of the ways one will try to make sense of it or formulate it is to use LP norms. The ratios of showing inequalities for ratios of LP norms tells you how spread the function is, whether it is peaked at one point, whether it is kind of evenly spread out, etc. Okay, so understanding that is important. Anyway, so that was a long story for a very trivial inequality that like this. Is okay?
Sir, question.
Yes.
Is the statement also true for like general P and Q with n raised to an appropriate power which is a function of P and Q?
You can try to use Holder inequality to interpret that, what it says and such things. So you can so you can try to interpret it using Holder inequality. I mean, I just wanted to give you an interpretation of what this would look like. I mean, so that this measures.
No, the original statement I meant, like you have one norm to infinity norm times one norm to infinity norm. In that case,
very good question. I will come to that a bit later. Actually, I will remark on it. Let's put it that way. Okay. So I will immediately answer another related question of yours. I mean, a question related to yours. What you ask is interesting. I mean, so you can ask all sorts of uncertainty principles. For any p less than q, can I give a PQ? This can be called one infinity uncertainty, where you can ask a PQ uncertainty, whether P norm of F to Q norm of F times P norm of F hat by Q norm of F hat. Can you give a lower bound for it in terms of something large, like a power of n? So that's an excellent question. It's not always true, not for every p less than q. It is true for a lot of pairs of indices. I may remark on it, but what I'll be interested in is one specific one for the moment. I will come to that. Okay. So postpone that point for a moment. Any other questions?
Sir, we have written norm of f2 upon norm of f1 minus 2. If we write reverse that, then like means norm of f1 square upon norm of f2 square.
Okay. Yes.
So
yeah.
Is it also the measure of spread?
Yeah. Actually, it's just the reciprocal. Okay. Does it go the other way? 1 second. What did I want to say? That if this quantity is large, it means it is more spread out, right? Okay. There, I said it the other way. Okay. Well, yeah. No, actually, you have a point. It looks like I said the opposite of something. Here, I said that L1 to L infinity norm is large if it is more spread out. That's right. Sorry. Actually, yeah. Sorry. I mean, I kind of maybe I made a. Yeah, sorry. I mean, you're correct. I mean, so I said the opposite. So here, L1 to L infinity norm is large if F is kind of spread out and is small if it is not spread out. What I should have said here was, okay, So it looks like I said something which is completely the opposite. Okay, I will leave you to figure that out. It's not, it's okay. All this is okay. But maybe you can just say from Cauchy-Schwarz inequality. So let me just say this, that what we know is that norm F1 is less than equal to square root n times norm F2. Okay, equality if and only if F is constant. That means norm F1 is smaller than norm F2 in general, and it is large when it is spread out. Okay, and when is it kind of small? If it is localized, then this what happens? It will be much smaller, right? So if F is delta x, it's not, then norm F1 will be in fact equal to norm F2. So like with the 1 and infinity. So, okay, so forget this motivation. Sorry, I mean, thank you for pointing this out. I said something which seems the opposite of what I wanted to say. But I will not try to explain that. Let's look at it like this, like Cauchy-Schwarz inequality. Norm F1 to norm F2 ratio is bounded by square root n. If it's localized, it is 1. The ratio of L1 to L2 norm will be 1. If it is spread out, it will be square root n. Okay. So let's take that as the motivation. So in general, we agree then that P to Q norm ratio measures the spread.
Okay.
Okay.
So
Thanks.
what is the meaning of localization?
Localized means it is kind of, well, we'll see. All this will be for, I mean, this is what, so I gave examples. I mean, I have not defined it and I have not used it. So it doesn't matter. Okay. So this
Okay.
itself, I mean, so see, there is a meaning in the real world which we have converted. So you can take this as a measure of localization. Once you understand this, in mathematics, we will declare that LP to LQ norm ratio itself is a measure of localization, one measure of localization. There can be others like entropy and other stuff. We can take other things. But the more concentrated, I mean, so just remember this example, delta functions are very localized and constant functions are highly unlocalized.
Okay.
Spread out, yeah.
Intuitively, in case of finite, like discrete case,
Yeah.
it's like every function should be like localized. Like this is just finite sum of delta functions.
Oh, yeah. But you have to do it with respect to the underlying space, right? So they also, in a finite space also, the delta function at a single point is localized. The constant function on the space is not so localized.
Yeah, what I'm saying, like this seems counterintuitive. I mean, in case of real line and all, that is fine.
Well, I mean, see, in real line also everything is a superposition of delta functions. So in some sense, all functions are superpositions of delta functions.
Yeah.
I mean, in a very generalized sense, it is always the case. So the difference between finite and the continuum is not so much that. I mean, see, you have to do it with respect to the space under consideration. And here you think of maybe n large for simplicity. So then it's the large space. And if your support of the function, if a function is supported on, say, square root n points, then it is kind of somewhat localized. Okay. Whereas the constant, somewhere in between the delta function and the full. Okay. Right. So you can have all such behavior. The difference in the continuum and the discrete setting is in the continuum setting, there is a notion of distance. In the discrete, we don't have a notion of distance. So two delta functions. So delta one, I mean, so if I have a finite set, if I take delta at 2 points, delta x naught plus delta y naught, then that is for me equally delocalized or localized, whatever you want to call it. It's wherever x naught and y naught are. Whereas in the continuum setting, sort of, you would think that these points have to be close for them to be localized, and if they are far, you may call them delocalized. But there is no notion of distance. That's the difference. Is okay?
Yes, sir. Thank you.
Okay, so now I'll come to the next uncertainty principle, very interesting one. Very easy also. Okay, so let me come back to this inequality. You remember L infinity norm of f is bounded by 1 by U10 f hat L1 norm, and f hat L infinity norm is bounded by 1 by U10 L1 norm of f. So now one other trivial inequality I write. I say that this is bounded by 1 by square root n so f hat infinity into SF hat. I'll say what is SF hat. SF hat is the support of f. Support of f hat. It is the set of all chi in G hat such that f hat of chi is not equal to 0. Similarly, support of f is the set of all x in G such that f of x is not equal to 0. Okay. So then you can bound this by 1 by square root n f infinity into the size of support of f. Why? I mean, this is a trivial very easy inequality. So how is that? Let me just write this one. It's exactly similar for this. So the left hand side is 1 by root n mod fx over all elements of G, but I can drop all the zeros, right? So I can just take over x in SF because the others anyway contribute 0. Now you see that that is bounded by, each of fx is bounded by the L infinity norm and the number of elements is SF, that's all. If you just used it naively, you would write norm f infinity times the number of elements of G. But that's wasteful. Let's remove all the points where it is 0 and write the rest. It's also a wasteful inequality, but we can use it's better. Is this okay? So a trivial inequality I use for L1, I bound by L infinity norm times the support size, and this L1 norm by L infinity norm times support size. Now you multiply these things. So okay, so now I write the next inequality. Second one. So now you look at this to this. Okay, so forget what is in between. Consider this and this and this and this. What is it telling you? The support size of the Fourier transform SF hat is bounded by L infinity norm of G by L infinity norm of F hat times square root of n. So let's write that down. I just copy that. I'll scroll back there to SF hat is greater than equal to square root 10 times L infinity norm F over L infinity norm of F hat. Right? Support F hat is bounded below by greater than equal to L infinity norm F to L infinity norm F hat times square root of n. And similarly, support size of F is greater than equal to this L infinity norm F hat by L infinity norm F times square root n. So let's write that also. So this is just copying from above. Now just multiply the two. To get the support of F size. Okay, by the way, this mod here means cardinality. Okay, this is it's overuse of the absolute value notation, but it's okay, it's standard. So cardinality of the support of F times the cardinality of the support of F hat. If you multiply the two, then the L infinity norms cancel and I get it's greater than equal to n. Amazing. So if F is supported on a small set, then F hat cannot be supported on a small set, right? So this is called Donohue-Stark inequality. they are statisticians. So they this was there is a application. I mean, so they discovered it in the context of continuous analogs of this were known. As I had mentioned earlier, although the finite case is actually simpler, historically always the continuous things have been studied earlier. In recent times, due to applications in computer science and other things, people have studied more and more of this in the finite setting, and many of those are simpler. As you see, this was an easy inequality to prove. Although this is not the proof they gave a proof which is more involved, and I have given it as exercise in the notes. You will see. So this is the Donohoe-Stark uncertainty principle, which says that support of f times support of f hat is at least 10. So that's so you may remember that equality can be achieved here. This cannot be improved. Recall, if n is p times q and the group is Zn and f is 1 on, let's say, 0 p multiples of p. And 0 otherwise. So let's say f is the, we had done this example before, f is 1 on the multiples of p and 0 outside. So then this would be, of course, the support of f. The support of f has size q in this case. Then, but we had computed that in that case f hat is, I don't want to worry about what that constant is. It was some non-zero constant on multiples of q. And that is the support of the Fourier transform. So in this case, the size of that will be p. And you see the product is actually equal to n. So you cannot improve it. This is attainable, and one can even prove a statement that essentially the examples will look like this. I say essentially, you can't say exactly this. There is one has to be a bit more careful. I mean, also, what is it in the general group? What will be this analog of this? So I don't want to go into the, probably I will skip the equality case. It's an interesting point, the equality case, but I will skip that point. And I mean, we will do something else which is more interesting, but I may skip that. Or if I feel like it, I will write it into the notes. Okay, any questions? So this is a very interesting inequality that f and f hat cannot be supported on small sets. This was the best. The example we saw was the best possible. Okay. Any questions, comments? Yeah. Okay. So now maybe I will go a little bit into what Sahasanand asked. So see, the point of inequalities is, so this is actually enough. So people who want can restrict themselves to this much. But the point about inequalities is it's very irritating when other people start talking about it, because then they will keep throwing at one inequality after another at you. And it takes, for me always, at least, I can't tell from perspective of some big mathematicians, but for me, when I take a paper and they throw lots and lots of inequalities, put this, that, etc., I get very confused. I try to catch on to one or two key inequalities and try to first assimilate that. But time and again, what happens, I find, is that once you assimilate that, then you start getting questions, just like Sahasanand asked, can we do this? Can we do that? And you go back to the paper. Essentially, that's what people would have done. So mathematicians somewhat think alike. I mean, that's not surprising. So that's essentially what happens. So, but it takes time to, at least for me, to assimilate these things. So what I now say, you can take it as optional if you want. If you don't want, you can ignore that. This is the interesting part. But what I want to, what is the other interesting thing I will go to, which probably I will do next time, or maybe even this time I will start. this is a kind of, so these things have applications also, as I said, in signal processing. But when you talk about the real world, whether a mathematical theorem says anything about a real world is a tricky point actually. So for example, take this inequality. Is it telling anything about the real world? Okay, let's say all these things make sense. So function is some kind of signal and Fourier transform is some meaningful thing associated to that signal also. This may be kind of interesting, but the fact is in the real world, nothing is ever exactly zero. Okay. So if you talk about a function on a finite set, every function will have support, full support. Okay. So no measurement is ever exactly zero. So this kind of inequality which says that if f is, so support here, only, so if everything is n and n, then this will be n squared, of course, even bigger than n. So then this is not saying anything. But the point is not that. The point, how to formulate in such a way that it can be meaningful in the real world also. You should formulate it in a robust way. Support is not a robust quantity. Okay, so a function can be 10 to the minus 100 at some point and it's still non-zero. Support takes that point. But practically, you will not count that as a point where function is non-zero. So this difference between reality and mathematics, how do you handle that? Don't talk about support size, talk about a robust version of support size, which I'll come to later. So we'll improve this inequality to some robust form, which is actually also a key style of doing analysis in modern times. So I will remark to that when we come there. But first, let me go back to Sahasranand's question. So what other PQ? Can we prove other PQ uncertainty principles? Okay, so one of the points I want to mention is that, so this second one looks a bit different, right? Support, but here is the what I want to convey first. That's why I introduced P less than 0 also. So one thing I want to say is, let me go back here. So there is no space. So let me go back here. So let me make one observation. See, f is from G to complex numbers. So look at norm fp to the power p, which is sum over x in G mod fx to the power p. Okay, what happens to this as p goes to 0? Now at any x where fx is 0, you will have 0 all the time. Any x where fx is not 0, that raised to the power p will converge to 1. So this actually converges to the support size. So support size is some way is related to the L0 norm. Well, I am being a bit loose because it's not, you have to raise it to the power p and take limit. If you don't take that to the power p, then I'm not claiming anything actually. So then it's not, I'm not claiming that this will converge to that. Okay, so it's after raising to the power p, it is converging. So but it is related to the 0 norm. In that sense, this is also an LP norm related inequality, except that p is 0 here. Here it was L1 to L infinity. This is something related to L0. One generalization I will show you immediately is, which will capture both, and it is a partial answer to Sahasranand's question. Let P be between 0 and 1. Then norm fp by, let's take norm fp by norm f infinity. Okay, this is some kind of a measure that I'll take this to the power p. This is some measure of the p to infinity. Okay, I have just raised it to the power p, that's all. Okay, if you want, you can put the power of p on the other side, so it's not a problem. Yeah, so here it is infinity to the power p is greater than or equal to some power of n. I think it is just n. Okay, I will, all the statement will be corrected when I prove it. Okay, so this, when p is 0, it will give you, when p is 0, we see that norm p to the power p is the support size, whereas norm infinity to the power p will become 1, power 0 will become 1. So you'll get support size of f times support size of f hat greater than or equal to n. When p is 1, you will get L1 to L infinity norm to the power 1, L1 to L infinity norm of f hat to the power 1 greater than or equal to n, which is the first inequality. So in some sense, this actually, it interpolates the, so p equal to 0 gives the second uncertainty principle, the Donohue-Stark, and p equal to 1 gives the first uncertainty principle, which doesn't have a name, I think. I don't know if it has a name. Okay. Okay, so how do we prove such a thing like this? Okay, how do we prove such a thing? Yeah, so so the idea is like this. You just use what did we do? How did we do the case? Okay, p equal to 1 is exactly 1, right? P equal to 1 is exactly 1, which came from the first inequality here. And what happened when p equal to 0? We bounded the L1 norm by L infinity norm times the support. So we want to do something analogous here. Okay, so let's just write that again. So there is a way to just cut and copy it here, but okay, I never did that, so I will write it again. So let me copy this again. Norm f infinity is less than or equal to 1 by root n norm f hat L1, and norm f infinity is less than or equal to 1 by root n. This norm f hat infinity is bounded by L1 norm of f by square root n. Now what we did earlier, so let's take this inequality. It is 1 by square root n sum f of x x in g. Earlier what we did was we restricted the sum to the support, and each mod fx we subbounded by the L infinity norm. So we got support size times L infinity norm. So it's kind of clear what we should do here. I want to get p norm here. Okay, p is between 0 and 1. Okay, p may be half or something. So what I will do is I will leave that much here. So we can do, so we will not pull out the entire. So you write this as fx to the power p, fx to the 1 minus p. So what I will do is I will bound the 1 minus p, power 1 minus p part like this. Okay, well, let me write it, then it will be clear. Times x in g mod fx to the power p. Is okay? Which is f infinity to the power 1 minus p times p norm to the power p, because p norm, this comes with a power, right? So p norm is 1 over p power of this by square root of n. So exactly the same thing works here and similar. So I will just bound this by what? I mean, f is replaced by f hat, that's all. Norm f hat to the infinity to the power 1 minus p. Norm f hat p to the p divided by square root of n. This is all we get. So now multiply this. You just divide by this. So what do we get? So this is telling us that if I divide it by norm f infinity here, this is telling me that, oh, rather, why write in the same line? So let me just multiply all this. So multiply the left hand sides and the right hand sides. Okay. So what we get it. So we get L infinity norm of f times L infinity norm of the Fourier transform less than equal to 1 by root n into 1 by root n become 1 by n. I have L infinity norm f hat to the 1 minus p, p norm of f hat to the power p. I have copied this quantity and now I will copy this. Infinity norm of f to the power 1 minus p and p norm of f to the power p. Okay, so now you cancel as much of the infinity norms as possible. L infinity norm of f cancels a bit, 1 power and L infinity norm cancels. So this immediately gives you exactly what we want. So this gives you n less than equal to, I bring n less than equal to 1 power cancels, right? So what you are left with is norm f p to the power p over norm f infinity to the power p. Norm f infinity to the power p gets left out, power 1 cancels. Okay, this is what I had claimed. This is the claim that p norm to infinity norm raised to the power p, p norm to infinity norm raised to the power p product is at least 10. If you want to write in terms of just this ratio, raise the power p to the other side. Like Sashanand said, you can erase it here and write n to the 1 over p. But at p equal to 0, that will not quite make sense. You have to understand it in the limiting sense. Okay, you can write 1 over p there, but let me leave it here. P equal to 0 has to be understood by taking proper limits. Otherwise, you will not. It will not make sense. So let's leave it like that. Okay, so this gives you p to infinity. So this is a p infinity uncertainty principle. You agree? It's a p infinity uncertainty principle. We can do p to q also. So let me go further. I mean, since I have only 4 minutes, I don't want to start the new thing, which is the real thing, which is the robust uncertainty principle, robust version of Donohue-Stark. As I said, for first timers, it's enough to stick to this one. And particularly Donohue-Stark is the interesting point that I wanted to convey. It's a non-trivial point. It's not obvious, and it is interesting and useful. Okay, so now we have put the P infinity uncertainty principle. You can also do PQ. Okay, so let me write a PQ uncertainty principle for suppose Q is between 1 and infinity. I don't know if 1, maybe you can take equal also, but let me for the moment not do. Want to get, so I am trying to get at a PQ uncertainty with P is still between 0 and 1 and Q is between 1 and infinity. Okay, so let's see if how to do that. The point is I already got P to infinity uncertainty ratios I got. So can I make a PQ uncertainty? So it's a simple point. So Q is between 1 and infinity. So you can write, you can write 1 by Q as a convex Q 1 by Q as a convex combination of 1 by 1 and 1 by infinity. What is it? It is 1 by Q divided by 1 plus 1 minus 1 by Q divided by infinity, right? So you are interpolating. This is the way you do in Holder's inequality, right? So if you want to think of Q, it's somehow LP spaces have been wrongly parameterized by P. They could have been parameterized by 1 over P. It's really 1 over P that you should write as a convex combination of these two. Okay, 1 by 1 and 1 by infinity, like this. Then Holder's inequality tells that I can bound the LQ norm by L1 norm to the power 1 by Q and L infinity norm to the power 1 minus 1 by Q, right? And similarly for the hat.
So that's a hat, right? The F hat.
Sorry, both are hats. Yeah, both are hats. So we have this. This is just Holder's inequality. I hope everyone is aware of this. Usually it's written, well, yeah, I mean, it's Holder's inequality, nothing more. This is Holder's inequality. So we get this. So how will I get an uncertainty principle for how will I get an uncertainty principle for P to Q norm? So let's see if I can do that. If I have norm FP, norm FQ, firstly I will write it as greater than equal to norm FP divided by this thing, norm F1 to the 1 by Q and norm F infinity.
It's 1 o'clock.
Okay, sorry, I have exceeded time. This is something kind of extraneous, so let me actually not postpone it to next time. Let me continue and finish, but people who want to skip it are welcome to leave. Actually, it's not highly germane to anything that we will do later, but I will take a couple of minutes and finish this off, okay? But you can also take this as an exercise. If you like even better, leave now and take this as exercise. Use this and the earlier inequalities to write a PQ uncertainty principle and later check whether you get the same as what I do here, okay? But I will just, for those who, is there anybody, I mean, is it okay if I stay and finish it off? I may take 3-4 minutes. Is okay or no?
Yeah, it's okay.
It's okay. Okay, so let's do this. So then I get this, and so how would I do that? So I already have this to the power P. Yeah, what do I have actually? So right. Okay, so norm FP. Right. Okay, so this we can write as best is probably to write this as norm FP by norm F infinity and then divided by norm F1 by norm F infinity to the power 1 by Q. So what I had earlier seen is that the P norm to infinity norm, I got an inequality, right? What is the P norm to F infinity norm? I got was, what was it here? Oh, sorry. Yeah, what this one? Yeah, this thing. So norm P norm to F infinity norm. What am I doing? Okay, so maybe I leave it like that. And then, so if you write the same thing for F infinity also, sorry, F hat also. Okay, it's possible that I will not get there. Now I'm slightly confused. The exact same thing comes out. norm f hat infinity, norm f hat p over norm f hat infinity into 1 over norm f hat 1 over norm f hat infinity to the power of 1 by q. See, the reason I have written like this is I already have the p to infinity norm, I have an inequality, and 1 to infinity also have an inequality. That's why I wrote like this, but both inequalities go the same way, which is why I'm getting apprehensive that I may actually mess up here. So if I multiply the two from these two, I multiply the two, I get norm fp to norm fq times norm f hat p to norm f hat q is greater than equal to, I get norm fp by norm f infinity times norm f hat p over norm f hat infinity. And then I have in the denominator norm f1 over norm f infinity into norm f hat 1 over norm f hat infinity to the power of 1 by q. Now this is what we showed is greater than equal to n to the power of 1 over p. That is the p to infinity uncertainty principle, which says that p to infinity norm, the product, is bounded below by n to the 1 over p. Unfortunately, this one also is a lower bound, so I can't. So this is I have to look. Is it true that this is greater than equal to this? Okay. Yeah. So it's, of course, this doesn't look meaningful because this, I have a lower bound for this. I also have a lower bound for this. So I certainly don't get this, right? I can't put that. But I think what one should do be a bit careful actually. So the inequality here for in terms of p norm and infinity norm is not just to infinity, but to also the L1 norm here actually. I should have been a bit more careful there. Okay. Okay. So I think the moral is that when you have 2 minutes left in the class, don't try to finish it. It's not going to work. So I will write it into the notes, but one can write an inequality for P and Q. So figure it out. The point is I should have used the middle inequality, that this is bounding one norm itself, not just the infinity norm. Then that will be better. Okay. So yeah, maybe I will not try to finish it now. I'll write it into the notes. But then you can ask further, what about P bigger than? So for can also get for PQ uncertainty for P between 1 and 2 and Q between 2 and P dash, where P dash is the conjugate. That is 1 over P plus 1 over P dash is 1. See, when Q was, yeah, so when Q is, the point is when P is 1, P, so yeah, so this is what one can get actually. So for P between 1 and 2 and Q between 2 and P dash also you can get, and various other things you cannot get. If I remember correctly, so I think if I remember correctly, okay, then it's not true for other indices. Meaning you don't get any meaningful bound. See, if you get a bound which is a constant, so norm, suppose you get a bound here which says it is greater than or equal to 20. That's not any useful because that means both can be localized, right? Even when you take a very large group, there is no increase in your conclusion. So that's not an interesting point. So the thing is, for other indices, you don't get something like that is there. I will write some of this into the notes, but as I said, concentrate on these two mainly, Donohue-Stark and the other one. Sorry for going over time, and I'll stop here.